To be able to measure the enthalpy of a reaction, we need a device that can measure the amount of heat change that occurs when one does a reaction, and this has to be done under constant pressure conditions. To do this, we need a device called a calorimeter. Calorimeters can be very sophisticated devices, but in essence, they are well insulated containers that have some sort of measuring device, the thermometer, and is open to the atmosphere in some way. So, as an example of a calorimeter that is relatively simple, it is possible to use two styrofoam cups that are nested together. This provides a pretty good insulating material, and that allows for external heat to neither go in or come out of the system that we're studying. Also, it acts as a good container because the solution in which the reaction can occur is typically placed within the cup. We also then place on top of this a cork that stopper of some sort that has inserted into it a thermometer and a glass rod that is capable of mixing to produce a homogeneous mixture of the reactants. In order to be able to measure the enthalpy of the reaction, we need to be able to measure the heat associated with the process involved for the system, and this has to be done under constant pressure conditions. We say that the Q of the system, in terms of if the heat is either being produced or consumed by the system, that heat is either coming out or going into the surroundings. And so the surroundings in the case of our calorimeter will be not only the cups, but also the liquid that is contained within the cups, and the system is the specific reaction. So it turns out that the Q of the system is negative of what the Q is for the surroundings. In this case, then, the surroundings is composed of the solution and the calorimeter itself, and so that the Q of the system is the negative of Q of the solution plus the Q of the calorimeter itself. But hopefully that Q for the calorimeter is minimal, so that primarily we're talking about the Q of the solution. And so in this particular case, we can make the statement that the Q of the system is the negative primarily of the Q of the solution. As an example of a word problem that you might encounter involving calorimetry, if we had a 2.78 gram sample of ammonium nitrate, presumably in the solid state, and it is dissolved in a constant pressure calorimeter, dissolved into an aqueous solution. The calorimeter contains 53.6 grams of water, and assume the specific heat of the solution is essentially the specific heat of water, which is 4.184 joules per gram degrees Celsius. The temperature of the calorimeter will change from 24.9 degrees Celsius to 19.8. So in other words, the temperature has gone down for the water. And this is an example then of an endothermic process. The question asks, what is the enthalpy of this reaction per mole of the ammonium nitrate? So in this case, the enthalpy is for the process of dissolving the ammonium nitrate. And we can state that the Q of the sample is equal to the negative of the mass of the solution itself, not the mass of the ammonium nitrate, but the mass of the water, plus the mass of the sample, and then multiply that by the heat capacity of the solution and multiply by the temperature change. So in this case, the mass of the solution is the sum of the two masses of the sample and of the water, and so we add those together and we come up with 56.38 grams for the total. And the temperature change, in this case, the final temperature is 19.8 and the initial temperature is 24.9, giving a negative 5.1 degrees Celsius change. And we plug those into our equation, and we have a Q for the particular sample that you'll notice is going to be positive. The negative from the equation and the negative in the delta T results in a positive value for Q, consistent with our endothermic process. And it turns out to be, with two significant digits, 1,200 joules. However, we haven't completely answered the question at this point, because we are trying to figure out the amount of enthalpy change per mole of the ammonium nitrate. So at this stage, we have the heat that was put into the system, which is our 1,200 joules, and we're going to carry along a couple of extra digits here. And so now we got to calculate our delta H in terms of kilojoules per mole. And so the first thing is, we know that the delta H is the Q divided by the moles. We first figure out our moles by taking the grams of the ammonium nitrate and dividing by the molar mass of ammonium nitrate, which is the sum of all the atomic masses in the formula. And we come up with 0.03473 moles with three significant digits. And also then we take our joules divided by that number of moles, and we recognize that then when we do the math, and there'll only be two significant digits, and the final thing is convert that into kilojoules by moving the decimal point 3 places to the left, and we end up with a positive enthalpy of 35 kilojoules per mole. Well, our calorimeter was a pretty unsophisticated device with the styrofoam coffee cups, but it is possible to use much better measuring devices. And what you see here is a schematic of what's referred to as a bomb calorimeter. It's often used to measure the heats of combustion reactions. What you have here is a very, very well insulated container that then holds some amount of water, and water will be part of the surroundings. Inserted down into that container is a second container that then holds the a cup of some sort that contains the sample, and this is referred to then as the reaction chamber. And in this case then we also can supply a source of oxygen into that particular chamber, and an ignition source, typically an electrical ignition source. And once the sample is ignited in the presence of excess oxygen, the heat that is generated within that container is then transferred into the surrounding water, and of course there's a temperature change, and this is measured using the thermometer that's inserted into the water. In addition to that, there's a motorized stirrer so that you then evenly distribute that heat throughout the water. In order to do various calculations involving the so-called bomb calorimeter, we have to recognize that the calorimeter itself is comprised of a number of different materials, so that we can't just simply go to a table of specific heats and look up the specific heat of the calorimeter. We would have to actually measure the specific heat for the calorimeter itself by doing a reaction where we know how much heat would be produced, and therefore calibrate and come up with the value of C for that specific calorimeter under the conditions that we're going to be doing our experiments. Once we have that value, then we can do the reaction for things where we don't know what the temperature changes would be for a particular reaction, and that would allow us then to use our calorimeter to do the calculations of heat and ultimately enthalpy of reactions. So, again, this is a situation that we have a constant pressure, so ultimately our change in energy will allow us to determine the enthalpy of a particular reaction. As an example of how to do a word problem involving a calorimeter, we have a 0.94 gram sample of an organic fuel, in this case octane, which might be a component of gasoline. And the formula for octane is C8H18. It was burned in a calorimeter, and previously the heat capacity of that calorimeter, the value of C, was determined to be 12.38 kilojoules per degree Celsius. So the temperature of the calorimeter plus contents increased from 22.17 degrees Celsius to 25.56 degrees Celsius. So this is a heat going into the surroundings from the reaction. This must be an exothermic process. Ultimately, we expect that our delta E and ultimately delta H will be a negative value. So it finally asks, what is the heat of the combustion per mole of octane? And we see that we have a balanced chemical reaction where 2 moles of octane react with 25 moles of oxygen to produce 16 moles of CO2 and 18 waters. Now, the first thing is we're going to calculate our heat. We're going to use our equation of Q of the reaction equals the negative of the heat capacity of the calorimeter times delta T. And our delta T value, the final temperature is 25.56. Subtract the initial temperature of 22.17. This gives us a temperature change of positive 3.39 degrees Celsius. And so in this particular case, we can plug our heat capacity and temperature change into our equation, and recognizing that when we plug that all into our calculator, we're going to get a negative Q for the reaction, and in this case it is negative 41.9, and with 3 significant digits we would need to round that up if we were to solve it at this point. Ultimately, to get the delta H of combustion, the enthalpy of combustion in kilojoules per mole, we're going to take our kilojoules that we just calculated and divide by the number of moles, but we've been given mass, 0.945 grams of octane. But in this case, then our heat is 44.41 kilojoules per gram. But now to convert that into moles, we need to take and multiply by the molar mass of octane. And we also have to recognize that the stoichiometry is such that we now have units of the kilojoules per mole. So with three significant digits, we have essentially 5,070 kilojoules per mole for this reaction.